Okay. Okay. Welcome everybody to EPSNA Summer School, the afternoon session of the day one. Afternoon first speaker is Dr. Okay. Would you please mute your mic if you're not the speaker, and unmute whenever you want to speak. So our first speaker in the afternoon is Dr. Solomon. He's a professor of physics at North Carolina A&T State University. And you can find his bio written in the bulletin, which is right on EPSNA page. If you go to summer school and right underneath, you can even download it as a PDF file. So he'll tell us about his research. Before that, Dr. Kassaun will tell you how to ask your questions.
Okay. Hi everyone, welcome back. So as before, if you have questions during the talk, you can use your phone to go to the EPSNA website or the bulletin, or I'll put it in the chat. But you can follow, you can simply go to this website here. It's in the chat.
I stop sharing.
Yeah, and okay, yeah, let me share my screen. Sorry. Yeah, so if you go to the EPSNA website and click on VSS 21, and you see the bulletin here. And in the bulletin here, it gives you information about how you can ask questions. So if you go to slido.com, and it will ask you to enter a code, and the code is right here. Sorry. The code is right here, this number, 653123. And if you when you enter that code here, it will bring you to a page where you can type your questions. And we'll monitor that, and that way our speaker can see your questions and address them. Also, if otherwise, you can also, near the end of the talk, you can go to the mic and mute yourself and ask the question that way as well, if you want to speak. Okay. All right. With that, I will let Dr. Solomon take over.
Okay, let me put up my slide. Okay, can everyone see this?
Yes.
Yes.
Thank you for the organizers for organizing such a wonderful course, and I'm really excited to share my experience and my research to the crowd. And again, this is a one-semester course, graduate course that I normally teach. So condensing this into a 1-hour program is extremely challenging, but I just want to give you a flavor of what I do, just to whet your appetite and encourage you to pursue this as one option in your career. You've seen the bio. I just want to emphasize here that my experience, my training is actually experimental and theoretical molecular and optical physics. So I did spectroscopy, laser spectroscopy, to study molecular interactions, chemical interactions, and collisions between atoms and molecules for a number of years. And then I moved to applying that background into atmospheric research. And so currently in my lab, I do use spectroscopic techniques and theoretical methods for atmospheric applications. And the focus in my case is actually looking at optical and physiochemical properties of biomass burning aerosols. These are particles that are emitted when there's forest fire, when you cook at your home using wood, or particles that are emitted in wildfires, in forest clearing, and so on, to understand their role in climate, weather, and air quality, urban heat, and health. So I do try to study optical properties as a function of photochemical aging, morphology, burning conditions, fuel type, influence of size distribution, and so on. So this is fundamental research that's done in the lab. We also try to expose in vitro exposure of lung cells to see the toxicity of those aerosols, to understand their health implications. I also do modeling work, which is really trying to extract the refractive indices of those particles by using electrodynamics theory, T matrix, and Rayleigh-Dunn and Rayleigh-Debye and Gunn theory, using high resolution TEM images of the sample. So I'll show you some of that as we move on. I also participate in field measurements. So these are aircraft measurements or mobile ground-based platforms to chase wildfire, and then measure some of the properties that we measure in the lab for comparison purpose. So this is purely interdisciplinary research. So my group actually consists of physicists, chemists, chemical engineers, atmospheric scientists, and we have epidemiologists and computational scientists. So it's not something I do alone. I have a large group of people that contribute to their expertise. So the chemistry is done by a chemist and at UNC Chapel Hill and other institutions. So we have a division of labor based on our expertise. And what motivated me to do this is really fundamental, because air pollution is estimated to kill about 7 million people worldwide. That's according to World Health Organization. And if you heard articles, COVID transmission has been enhanced in areas where the air quality is very poor. Death rates from air pollution are highest in the low and middle income countries. And it's 100-fold difference in the rate across the world. So what you observe in Addis Ababa recently, the excessive flight delays due to haze and fog, is a result of air pollution. It's really chemical reactions of emissions, pollutants in the atmosphere that combine with the meteorology that creates all this dense fog that has forced planes to divert and delay for the last several weeks in the winter. They also lead to complicated health conditions like asthmatic attack, heart attack, lung cancer, stroke, chronic COPDs, and so on. And actually, recent studies link air pollution to Alzheimer's disease. This is Proceedings of National Academy of Sciences, a very recent article in 2021. There is accelerated decline in memory associated with long-term exposure to PM 2.5. These are very small, 2.5 micron and below particles that are emitted in smoke, or air pollution in general, because air pollution comes not only from biomass smoke, which I'm focusing on, but it comes from diesel emissions, it comes from trash burning and other natural sources. And it's also linked to dementia and cardiovascular disease. So there is really societal relevance to what I do, and that's really what motivated me to shift my research. So you can either do basic research, which is very exciting, but at the same time, you can also do applied research that will have societal relevance. So the choice is yours once you decide what research you want to do. And this is actually a statistics that shows you air pollution is the fourth highest risk factor in causing deaths across the world in 2017. So this is a serious issue that needs serious attention. So that's what really motivated me. So the outline in this talk, I'm going to talk about available techniques and environmental constraints for fieldwork. This is to show you that you can do very simple and very clean experiments in the lab, but what happens when you go to the field? When you're flying instruments in an airplane or mobile platforms, what are the constraints and the difficulties associated with that? Then I'll focus on spectroscopic applications for gas detectors. This is infrared spectroscopy, chemiluminescence, or fluorescence techniques. Then I'm going to explain optical techniques like cavity ring down spectroscopy. That's what I use in my lab. And then scattering of light using nephelometry. Then we have photoacoustic systems to measure absorption of light by particles. So available techniques include mass spectrometry. This is an old technique, very precise, sensitive method. Very simply, just ionize particles, accelerate them by electric field or magnetic field, and measure their intensities. And then you have gas chromatography, another old technique for airborne applications. Measurement is intrinsically slow due to transient time. You can also think of chemical methods. Wide variety of chemical analysis can be performed to determine concentration. This is not an online method. Samples must be taken out of the experiment to be analyzed, so there could be errors associated with transport, handling, and so on. We have solid state sensors based on observing materials which change one of their physical properties in the presence of particular molecules. So they could change color, for example, or they could change some of their chemical properties. Then you have the optical techniques, measurements that rely on effects of light sources on samples. So this is what I'm going to focus on. Detection of which are induced. So you can detect in phenomena that are induced by absorption of light, laser-induced fluorescence, for example, or ions-enhanced multiphoton ionization is another method, and so on. So these are the disadvantage is calibration procedure. It's not self-calibrating measurements that depend on the effect of the sample on the light. So there is limited sensitivity in some cases. So I'm not going to discuss all of them, but just to give you an idea of what's available. So optical techniques include photoacoustics, laser-induced fluorescence. Photoacoustic is energy is absorbed by photons. Photon is converted into kinetic energy that results in pressure fluctuations, and pressure fluctuations cause acoustic waves. So the pressure in the cell is modulated at frequency. A sensitive microphone is on the side detects the pressure change, which represents acoustic waves. That's how sound travels. So you're using the properties of sound in order to do photoacoustic techniques. Laser-induced fluorescence is an old technique in which sample absorbs light, and light is emitted at a lower frequency. Each molecule has its own emission absorption properties. So by looking at the emitted light, possible direct detection of absorbers can be done. Its very high sensitivity can be achieved. You can study up to 1.8 times to the power 8 molecules per cubic centimeter in the upper troposphere. Then there is direct absorption. This is a more straightforward technique where laser frequency sweeps across a molecular absorption. A detector converts the received power into an electrical signal. By measuring that fraction, you can measure the light that escapes. So it's a summary of what those are, and I'm going to provide the slides later on because I may not be able to go through all of them today. So what happens when you go to the field? There are a number of problems. The outside world is harsh, unlike laboratories. You have to protect the instruments. Power supplies cannot be as big as what you use in the labs. There is possible different line voltage on board aircrafts and vehicles. The ambient temperature could be different because there is a wide range of temperatures depending on where you are in the atmosphere. You cannot have optical tables with tuned vibration absorbers that you have in the lab. So there are a number of problems associated with environmental constraints. There is thermal drift of many components, temperature effects, mechanics, and optics, obvious size changes. There's an echo. And you can go on environment, there are no clean rooms in the environment. Corrosion is a problem, no pressure stability, leading to poor mechanical stability. And these are some of the constraints that you encounter in the atmosphere. So what's spectroscopy? Again, just to simply define this, it's the study of spectral information. You have a physical stimulus, that's a molecule, absorbs light, it responds, and then you have a detecting instrument that detects the light emitted. And all of you by now know what the electromagnetic spectrum looks like in frequency space, in wavelength space. And these are the scales to which these wavelengths are associated. So you have in the microwave, infrared, visible, and then you have the gamma rays, X-rays, which are very short wavelengths. But mostly what we do is in the optical spectrum between 400 nanometers. This is the setup I'm going to describe where optical spectroscopic techniques are applied. The lab consists of a smoke chamber. This is a tube furnace where we create the smoke. So we put a small amount of wood sample, we burn it at different temperatures, and then we measure the carbon monoxide, the carbon dioxide that's emitted during burning. That gives us the burning conditions, whether it's smoldering fire or flaming fire. And then we measure the NOxes, the nitrogen oxide components that are emitted. The smoke is introduced into a smoke chamber, which is about 9 cubic meters Teflon bag where the smoke is introduced, and you have UV lights to simulate real atmospheric conditions, meaning sunlight. So we have UV light banks. So when we turn the UV light, we initiate chemical reactions. And then we can measure, we can take filter samples out of the chamber for TEM, transmission electron microscopy analysis. We have we measure the humidity in the chamber, we measure the temperature in the chamber. The particles are then removed from the chamber. They go through differential mobility analyzer that classifies the particles by size. And then we use scattering technique to measure the number of particles in the sample, so we can count them based on size. This is a dryer. If we are using humidity, then we can dry the particles as they go through a dryer. Then the particles are sent to a photoacoustic system to measure how much light they absorb. The cavity ring down system measures the extinction of light. The nephelometer measures how much light they scatter. So by understanding how much light they scatter or absorb, or by measuring the extinction, you can determine what's called their single scattering albedo that tells you whether aerosols contribute to the warming or cooling of the planet. We also measure the mass. This is aerosol mass particle analyzer. We also try to measure the condensation particle counter, measures the particles that are responsible for cloud formation, because one of the properties of aerosols is they serve as cloud condensation nuclei. So you have to have aerosols in the atmosphere in order to generate clouds, and the clouds are what give us the rain. So water particles, molecules can be deposited on the surface of aerosols. So by looking at the cloud condensation nuclei character, we can also understand their properties. Here is another instrument that we use, SESM. This is aerosols composition speciation monitor that measures the inorganic compounds that are emitted during emissions. So this is the physical nature of what the lab looks like. So what I call a cavity ring down system is this long tube. These are the laser systems. The nephelometer is that measures scattering. We have all the gas analyzers on this side, the furnace, and the smoke chamber looks like this before it was covered while under construction. So as you can see the UV lights, but at the back in the lab here, there is a smoke chamber. So as I indicated, going back, I'm going to describe how those gas analyzers work and how spectroscopy is used in analyzing those instruments, how they operate. So you'll see the application of spectroscopy there. You'll also I will also go through the scattering techniques that is used in condensation particle counter. That's the device we try to use to count the number of particles at a given size. The nephelometer uses scattering techniques to measure the scattering of light. So again, this is electromagnetic scattering from matter. So it's the theory is very straightforward. I'll try to show some of that. And then I'll describe the cavity ring down system in more depth, because that deals with Gaussian beams and cavity mode matching within the cavity and so on. And then I'll talk about the photoacoustic system at the end. So mass gas analyzers, these are some of the gas analyzers that we have. This is carbon monoxide monitor. This is an NOx monitor. They all look alike physically, but they use different principles. So interaction of matter with electromagnetic radiation, that's UV, visible, or infrared, or X-ray and gamma rays. Or we can use absorption spectroscopy, where target molecule absorbs the light, or we use emission spectroscopy too. So the basic principle is straightforward. We use what's called Lambert-Beers law. You have light source. This is the incoming intensity. This is the cell where the particles or gas are located. That is the length. You could take a differential element of that. And this is the intensity that's transmitted and that's detected by the detector. So you can easily see the maths, very simple. There is an exponential decay. Alpha is absorption extinction coefficient. And the cross-section is obtained by multiplying the extinction coefficient by the number of absorbing particles. So sigma, if sigma is known, then n can be, the number of particles can be determined absolutely using this technique. This is just another way of presenting the same idea. So in IR absorption, for example, when you have CO, when in detecting carbon monoxide, we depend on IR absorption. So this is absorption at when there is no gas, there is no signal observed, but when there is a gas that's absorbing the light, you can see a dip in the spectrum that shows you the presence of. So CO and ozone absorption they use the technique that I just described. So this is absorption tube in the absence of any gas. And then you repeat the same thing with either ozone or carbon monoxide in there. So you just change the sample and determine the light that's coming out in order to determine the concentration of either carbon monoxide or oxygen. So this is a simple absorption technique, which is straightforward. Then we also try to measure sulfur dioxide, which is really a very nasty chemical that's emitted in power plants, in biomass burning, it's also emitted in diesel emissions, mostly in industrial emissions. And in this technique, we actually excite the sulfur dioxide molecule using a UV light at 214 nanometers. So you generate an excited sulfur dioxide molecule. And then the sulfur dioxide excited molecule doesn't stay, it's not stable. So it gets de-excited, comes to the ground state, and emits light at 330 nanometers. So it comes to the ground state at higher vibrational or rotational level in the signal at 330 nanometers is a function of the intensity of the initial absorbed light. So absorption coefficient of SO2 has been determined, so you measure the decay rate. So this is really the technique, excitation. These are typically, if you have a molecule, this is a two-dimensional diatomic model for a vibration, electronic state of a given molecule. This is an excited electronic state, and within electronic states, you have the vibrational states, and each vibrational state has a manifold of rotational states. So these are coupled states. So you can have light absorbed, and you detect in the red, that's the fluorescence of the excited state. So this is basic atomic spectroscopy. So in this case, we were doing field measurement using an aircraft. So this is SO2 UV fluorescence detection in the C-130 airplane. This is what it looks like inside the airplane. So this is really a flying laboratory. This is one of my graduate students working on putting in liquid nitrogen in one of his devices. So this is a flying laboratory, basically. These are different rack-mounted instruments measuring different aspects of the atmospheric emissions. So the fluorescence spectrometer is shown here. You have a UV light, a mirror assembly, and then you have a photomultiplying tube. So these are different electronic devices. So you're actually, basically, you're exciting the sulfur dioxide molecules, and you're looking for the emission from those sulfur dioxide molecules, as I indicated earlier. And so you're looking at specific vibrational states of the molecule. This is very important because sulfur dioxide can be emitted from volcanic emissions, ocean sulfur cycle, or forest fires. It can be emitted from power plants, transportation, diesel, and wood burning. It has so many different sources, or it can come from transportation, like when you have these big ships carrying lots of containers across the oceans, they emit lots of sulfur dioxide. Traffic, of course, I mentioned, home heating. So they have very nasty properties. They are corrosive, so they lead to what's called acid rain. And their impact could be destroying natural heritage, like the decay of historical heritage is based on atmospheric sulfur dioxide. So that's another toxic pollutant. So that's one of the techniques. Fluorescence techniques are used for measuring sulfur dioxide, whether you're doing it in the lab or in the airplane. And then we have what's called the luminescence technique. This is emission of radiation which occurs during returning of excited molecules to the ground. So chemiluminescence specifically is excitation is caused by chemical reaction. So you're not using any light source in this case. So there's some chemical process that excites the molecules and they emit to the ground state. So chemiluminescence techniques are used in measuring NOxes. So nitrogen dioxide, for example, is used. It uses chemiluminescence. As a result of collision between NO and ozone, you get excited molecule of NO2, and this decays into NO2 plus oxygen molecule, and then dominant pathway is the formation of NO2. So by looking at the different emissions, this is a photomultiplying tube, you can detect the NO2. And then I'll move on to the cavity ring down technique. This is a very sensitive technique in which the rate of absorption rather than the magnitude of absorption of light pulse confined in an optical cavity is measured. So the sample in this case is placed between two highly reflecting mirrors, and a short pulse is coupled into the cavity. So instead of measuring the total intensity of the light exiting the cavity, one determines the decay time by measuring the time dependence of light leaking out of the cavity. This is a very sensitive technique because you're measuring rate of absorption rather than magnitude of absorption of light. Instead of measuring total intensity of light exiting the cavity, we are interested in the decay time by measuring the time dependence of the light leaking out of the cavity. So absorption in this case is determined from the time behavior of the signal. It's independent of the pulse-to-pulse fluctuation. That's a big advantage because your lasers may not always be stable. So this measurement is independent of the pulse-to-pulse fluctuation of your laser. Its effective absorption path lengths could be as long as several kilometers. So by confining light in a cavity of a short distance and allowing the light to bounce back and forth millions of times, you are actually replicating path lengths of up to kilometers. So it's a very effective technique. So it's absorption technique. It's very simple to build. Actually, one of my graduate students built the cavity we have in my lab. So this is what I was talking about. You have a laser light, you have a pulse that goes through the cavity, it bounces back and forth, but some of it leaks out because these are highly reflecting mirrors, 99.999% reflecting, but a small percentage leaks out. But with every round turn, the amount of light that leaks out or the intensity gets smaller and smaller. So this is the initial pulse that comes out. The next one is of lower intensity, and it keeps going. So the power of the transmitted pulse is given by this expression. Alpha is the coefficient, the absorption coefficient. So when the laser pulse with power P naught is sent through the optical resonator of length L of these highly reflecting mirrors, the pulse will be reflected back and forth between the two mirrors, while each round trip, a small fraction will be transmitted through the mirror and can reach the detector. So the detector receives a series of pulses separated by a round trip time, which is twice the length, at twice L divided by the speed of light, with decreasing power. So this is, each beam is traveling to L, and the time it takes for this travel is 2L divided by the speed of light. So you can go on and derive the time, the decay time of this in the absence of, in the presence of any particle in the, or gas, or in the absence of gas where the cross section is 0. So these are the time constants, tau 1 and tau 2. And you are interested in, from the difference d tau, which is tau 2 minus tau 1, the product can be obtained. So this is essentially, I'll go on and show you what it looks like. So basically, this is the system. You have a laser pulse. I'm not going to go into the details of what those stand for, but the point is, you have a 355 nanometer pumps the OPO. The OPO is actually a solid state system which emits light between 400 and 800 nanometers. This light is steered through a series of mirrors, and we have a telescope over here. I don't know if you can see this. Yeah, this is a telescope and the turning mirrors. And so the point is, we want to match the mode of the cavity to the laser mode. In other words, the spin hole shows you the beam waste, and I'll have the notes in more detail about what this beam waste means, has to match with the beam waste being at the center of the cavity. And then the light that's leaking out is measured using a photomultiplying tube. So this is the details of the derivation. You have an absorber. In the absence of an absorber, again, we are using Baird's law, which is absorption technique. We measure the differential cavity loss, integrated cavity loss. I wish I had the whiteboard to write this and show you how, but this is a very simple derivation. Most of physics students easily understand this. But this is really the key. The key fact number that I'm interested in is the cross section. The absorption coefficient and the cross section are related by this equation. So notice here we have 1 over tau and 1 over tau 0. And this is very simple here. Again, I'm reproducing the same figure. You have a beam coming in, bounce back and forth. You can see by the showing the thickness, I'm showing the intensity is getting smaller and smaller as it leaks out. So you have this decay profile. So the two decay profiles are different with a sample and without a sample. So the ring down time, as we call it, tau 0, is a ring down time in the absence of a sample. And this is a ring down time in the presence of the sample. By looking at the difference, you can determine the extinction coefficient. So here, incoming laser beam has to be mode matched to the fundamental TM00 mode, resonator mode, otherwise transverse modes is excited with higher diffraction loss. And then these are some of the conditions that are required. So when I say TM00 mode, this is basically a Gaussian mode. And this can be, I'll show you the slide, roughly goes through the slides where one can see how those modes are derived. These are really Hermite polynomials of a simple harmonic oscillator. And the cavities can be constructed in a number of ways. You have a 2-mirror cavity where you have only 2 mirrors. There is a triangular cavity where you have 3 mirrors, and there is what's called a bow tie cavity. But I'm going to give you some idea of how we do the mode coupling. So this is a simple example of a tunable laser. This is a telescope that I mentioned in the earlier slide, where the beam is focused into a pinhole, and then it spreads out, then it hits a mirror. And the idea is to have this beam in such a way that the beam waist is located at the center of your cavity. That's what I mean by mode matching. So in order to do this mode matching, you have to consider the different optical components and the ABCD matrix of each beam. So what's the ABCD matrix? It's really a very simple idea where if you have a beam, this is if you use ray diagram of a beam of light, it makes an angle theta, and it's a distance r as a function of z, which is z is along this axis. And so at a distance d, the angle here is actually the slope of the beam. After a certain distance d, the beam is not really deflected. If it's not deflected and if it's moving in a simple straight line path, the slope doesn't change. So the slope at z2 has to be equal to the slope at z1 plus the distance between the 2 points, which is given by this equation. The slope at both points is going to remain the same. So from this, you can determine a matrix that connects the beam at the starting point to the beam at the end point by this simple equation. This is called the ABCD matrix in optics. And you can have ABCD matrices derived for lenses. This is what you have for a length of focal length f. And you can have ABCD matrix for a mirror given by the radius of curvature r, and so on. So when you apply this, for example, to 2 mirrors, you'll consider 4 matrices for the system. So there is a mirror here, another mirror at this end, and the beam goes back and forth along this path. So the 2 mirrors have different focal lengths, R1 and R2. So the matrices are going to be different. So so you start from a beam going straight from one end to the next mirror. That's this matrix. Then it's reflected by a mirror. This is a matrix that allows you to describe the interaction of the light with the mirror. And then straight path going back, described by this one, and then another mirror. So you have these 4 matrices that needs to be multiplied. So this is the ABCD matrix for a 2-mirror cavity system. But the light that's trapped in this cavity bounces back and forth millions of times. So if you take the power of n of this for n round trips of the beam, then you take the n power of this system, and after some derivation, which I can provide in another slide, you can see that there is what's called the G parameter, which is related to the distance between the mirrors and the radius of curvature of the 2 mirrors. So, sorry, this is mangled up. This is less than or equal to, less than or equal to. So between 0 and 1, the product of this is a G parameter describes whether the given cavity is stable or unstable. So this is unstable region. This is a stable plane. Mirrors are stable. You can have unstable region here and stable. So you can determine whether your cavity is stable and maintains the beam to bounce back and forth indefinitely by measuring the G parameter, which is derived from this equation. So when you apply this to the cavity that we're using, then you have to consider the thickness of the lenses. So in that case, this gets a little bit more complicated because this is the refractive index of the mirror material and the air surrounding it. So this ABCD matrix can get more complicated. So for the ABCD matrix for CRDS is given by this expression. So in optical cavities, these are again some more details that need to be understood. Cavity transmission And there is a free spectral range, which is the distance between the cavity modes, and the full width at half maximum is expressed in terms of the radius of curvature of the mirrors. This is again an alternate way of deriving the same thing by thinking in terms of the photon lifetime in an optical cavity. So I'm not going to repeat this. So the sensitivity, the minimum detectable cross-section is given by this expression. But the key is there are certain limitations. There is mirror reflectivity, best achievable is about 5 parts per million in detection limits. The cavity length is another factor that needs to be considered. And then when you're applying this to measure extinction of particles, one has to think in terms of the other absorbing and reflecting particles. So these are gases, but they follow what's called Rayleigh scattering because they are smaller than this wavelengths of light. So in calculating tau naught, the ring down time, one has to consider all these factors. There is a mis-scattering due to particles. There is interfering absorption. There is Rayleigh scattering. There is a mirror transmission and empty cavity loss. So all those have to be taken into consideration and they contribute to the error. But most cases, these are very small corrections that don't really impact the measurement. And the other issue is the mirror reflectivity is a key. You have to have custom-made, highly reflective mirrors to accomplish this task. And they don't come cheap. Each of these mirrors of 2 centimeter diameter are about $2,000 a piece. So they are very expensive, and the procedure for cleaning them is equally very delicate because you want to make sure the light is not absorbed by the mirrors. And you have to purge. In the cavity ring down arrangement, you have to continuously flow nitrogen in order to keep the mirrors as clean as possible while running experiments. So these are not cheap experiments. So one of the key things is this is a spectral range of the laser beam. I mean the cavity, but this is a bandwidth of the laser. So the idea is you need to have more broadening occurs as delta T becomes smaller than the transmission time. So this is some more detail. This is line width effects. This is spectral line shapes. That's another important. So mode beating, this is another thing that one needs to be very careful in designing those cavity ring down systems. Mode beating is a result of a mismatch in the cavity mode and the laser mode. So when you have mode beating, you'll get this kind of interference instead of a straight line. So the alignment is really the most critical part of this work. You can use continuous wave lasers or YAG lasers for this system. So example, you can use diode lasers, for example. Most of the cavity ring down systems that are used in the field for aircraft measurements or ground-based measurements, since you don't have a stable optical table, you can't have those large lasers that you saw in my lab. So you have to use single frequency diode lasers or helium neon lasers or argon ion lasers for field measurements. But the neodymium YAG are bulky and they have to be put in a stable table. So there are different ways of accomplishing this. You can either use CW, that's continuous wave, or pulsed laser sources. These are some of the examples that, for example, molecular absorption. These are the different molecules that can be absorbed under visible near IR. For example, near IR for most small VOCs, these are volatile organic compounds, HO2, and any of those can be accessed using IR, the mid-IR, and of course, visible light. You can have nitrogen oxides, glycosol, water vapor, and these are some of the properties. And then for UV, you have ozone, aromatics, and halogens. Okay. So this, again, this cavity ring down system has a number of interesting applications: measurement of small absorption cross sections. Now you can do chemical kinetics using cavity ring down systems, laboratory measurement of radicals, and field measurements, atmospheric trace gas detection, and aerosol extinction. So I'll skip this. This is the field component that's used by the NOAA Earth Systems Research Lab, and it's called Airborne Ring Down Nitrogen Oxide Laser Detector, and simply called Arnold. And this is Arnold Schwarzenegger, that the actor is depicted to represent this device. So this is a multi-cavity system using light sources that are portable, so single frequency wavelengths. They flew on the NOAA Hurricane Hunters to detect all these chemicals. Of course, extinction, again, this is what I wanted to show you. In my work, in my lab, I'm interested in this quantity called albedo. So we measure the extinction, the ratio of the scattering to the extinction. So albedo of 1 means, close to 1 means that the particles scatter significantly. So if the particles are scattering, they contribute to the cooling of the planet. If the albedo is very low, which means scattering is smaller than the extinction, then you have more absorbing particles. So when light is absorbed, there is more heat trapped, and so they contribute to the warming of the planet. So in my lab, we try to measure the effect of different environmental and meteorological conditions on the optical properties of those aerosols formed from smoke that's emitted in cooking at home, or wildfires, or forest clearing, and how do they contribute to the warming or cooling of the planet. So that's one aspect of the research, where you look at the climate impact, radiative impact of aerosols in the atmosphere. The other aspect is to look at how they impact health. So you look at the particles. So the fresh particles emitted from fire are used to expose in vitro lung cells, and we age the particles by letting the light on, so they chemically get transformed, and then do the exposure again and see which of those are more toxic to human health. And there is no such thing called fresh smoke in real atmosphere, because as soon as the smoke is emitted into the atmosphere, it immediately interacts with whatever is up there. So most significantly, in the African megacity environment, the emission standards are very lax. So you have lots of NOx emitted from old cars that are on the streets. You can feel it when you go down there. And then you have trash burning, which is a big source of toxic volatile organic compounds and toxic minerals. Plastic burning contributes significantly to very poor air quality. So all these extinction measurements and the scattering properties of these particles also allow you to see what is the impact of aerosols on the visibility and the formation of haze, formation of fog is related to the chemical reaction that takes the extinction and the scattering of particles in the atmosphere. So again, that's an environmental hazard that one needs to clearly understand. So how am I doing with time?
You have about 9 more minutes, and then there will be 15 minutes for Q&A.
Okay, so I'll just have to run through. Again, will the slides be available to the students?
Yes, if you're willing to share them, we'll
I'll send it to you. Yeah, because I can. So this is, as I said, this is a semester course. So I'm trying to condense it into a small segment so you can see what's involved. So again, in order to understand Gaussian beam theory, you have to do the electromagnetic wave propagation under what's called Helmholtz equation. So I'm going to skip all the slides in the interest of time. This is how the Gaussian beam mode matching works. So there is more detail here. So I'll skip this. Then I talk about light scattering is another particle sensors. We have inexpensive light scattering for large particle masses, condensation, nuclear or particle counter. We have optical particle counters, and then you have all this use scattering of light. So one of them is the cascade counter. So what this does is particles coming in, the smaller particles are allowed to go down, the larger particles get impacted on each plate at each surface. So this is cascade impactor, we call it cascade impactor. And you can get particles at different sizes at different stages of this impactor. This is how we do particle selection by size. And the particles absorb water, and they are measured or counted by the scattering of the light that they do. And then the nephelometer is another device that measures the scattering of light at different wavelengths. These are the detectors, some of it is transmitted. This is what a nephelometer looks like. Scattering is measured at 3 wavelengths. That's and again, this is based on theory of scattering of light. Let's keep this. This is basic electrodynamics, except now you have to deal with the solutions in terms of Legendre, Bessel, and Newman functions. And then you have to relate them to by series expansion of E and H. I'll skip this to show you why we need this. So again, this is meant to derive theoretically what I'm interested in, those cross sections, scattering cross section, extinction cross section, based on me theory, that's the scattering of light by spherical particles. But most particles are not spherical, they are fractals, so you have to use what's called the T-matrix theory. Again, the interest is to calculate the extinction and the scattering. This becomes very complicated using T-matrix when the particles are. So these are what we look at. Basically, this is the type of particles we see. When we collect them on filter samples, depending on the burning condition, for example, in some cases, you have nearly spherical particles when the burning is smoldering. So you can apply me theory to understand their scattering properties. But when they are fractals like this is smoke produced at high temperature. So it's called the flaming fire. That's what you observe mostly from wildfires. So these are very, very small particles connected as fractals. And so their scattering and absorption properties cannot be described using me theory that's strictly applicable to spherical particles. So in this case, you have to use what's called the Rayleigh-Debye-Gann theory to understand their scattering and extinction. So that's what we did in some of the work in my lab. And finally, the photoacoustic system, which is really, I'll give the slides. It's a very long derivation that one can look at. Optical absorption results in the production of excited states. Then you take the 2-level system, which involves the ground state and the excited state. So this leads to an elaborate theory of absorption. But the point is, you can use a photoacoustic system, which is really a very sensitive technique to measure absorption independently. We can measure extinction, which is the sum of absorption and scattering, using the cavity ring down system. You can measure scattering directly using a nephelometer. So from those 3 properties, one can determine the radiative impact of aerosols on climate. But at the same time, you can also look at the optical properties. How do those optical properties change under humidified conditions? And this is very important because most of the tropics is humid. So under humidified conditions, how do the chemical and optical properties of those particles change? And that's very important to understand the impact of aerosols in the tropics. And Africa produces the largest biomass burning aerosols in the entire universe, in the continent. So it's very critical to understand the impact of aerosols, biomass burning aerosols in the tropics. So that requires understanding their hygroscopicity, that's their water absorbing properties, and how they change with how their optical properties and chemical properties change with increased relative humidity. That's also related to their cloud condensation nuclei implications. So that's another interest that we do in my lab, where we measure the cloud condensation nuclei properties. Another thing I didn't mention is most of the fuel samples we burn in my lab are African fuel samples. So we have eucalyptus, we have cow dung, because it's a major source of fuel in Africa in most rural households. And cow dung is another, has very interesting chemical emissions, toxic inorganic chemicals that are emitted when you burn cow dung. So we're trying to see how they contribute. And we find out that they're also very critical in cloud condensation nuclei, because they form smaller particles. And we also use GRAR, that's acacia, Waira, and I got all those wood samples. So we try to measure the emission factors of these particles, because the emission factor is really very critical in air quality management systems. EPA uses that to regulate the air quality in the US. So, but none of those are measured for African fuel samples. So that's one of the things we do. We just have a recent paper that measures emission factors of about 12 fuels from Botswana and Ethiopia and East Africa in general. So I guess I better stop here and entertain some questions, because I'll have the slides available for everyone to go through later on their own time. And again, this is a whole semester course, and it's not, I'm not doing justice by rushing through it, but the point is to expose you to what can be done. And my main message is, you can determine what you do with your physics. You can do very good, interesting, fundamental science that would advance human knowledge, and the application may not be immediately obvious. Or you can use your physics skills and work with other disciplines to do your studies in applied research, that like the one I'm showing you. In my case, I haven't abandoned my basic science research, but this is applying what I know in basic physics and chemical physics to understand an environmental problem that's of significant importance. And we also try to couple this with what's called urban heat islands. So there is a coupling between urban heat and urban pollution islands. They contribute, and they create some kind of feedback. So urban heat is another major problem in society, because urban areas are more heated than the surrounding areas, because there is no green space. Most of the asphalt is absorbing. There are cooling and heating and refrigeration that spew lots of heat into the environment. And the recent heat wave that you are observing in the Western United States and now in the Mediterranean countries is leading to major health impacts as a result of the creation of urban heat islands. So again, these are environmental issues that impact human health, human life. So how do you apply your basic science and physics training, work in an interdisciplinary manner to advance the needs of society? So I guess with that, I will leave it there.
Thank you, Dr. Solomon. And is there any question? Are there any questions? If not, we'll go to the next speaker.
There is one question that was posted on the online question forum. It's from Olefata. I will try to read the question. It says, why light emitted by a laser while emitted by an ordinary light source is not? I'm not sure I understood the question. Yeah. But maybe you okay, maybe.
Yeah, I think it's probably, yeah. So the difference between a laser beam and light is, laser light is unidirectional. So if you have a light source at a given point, you have spherical waves spreading out in all directions. But a laser wave, a laser beam is has single direction, and it's a focused beam, so it's unidirectional. So you cannot use ordinary light because it's not focused. And again, the whole derivation of this idea of how to approximate, because when you solve the wave equation in general, you have actually I should be there is no short way of getting there, I guess. Yeah, here is what I was trying to, and I'm almost there. Yeah, so this is what you have. You make lots of approximations to describe what a laser beam looks like. It comes from this. Okay, one more step. So this is a general electromagnetic Helmholtz equation. So when you look at, normally you have a spherical wave that's spreading out in all directions, but you make an approximation so that you have a beam. Wait a second. So this is the general expression of the solution of the electromagnetic wave when you have a Gaussian beam propagating in one direction. So the whole point is you cannot use ordinary light source because it's not unidirectional. It has multiple wavelengths. The laser beam can be tuned to a specific wavelength. So white light has all wavelengths mixed up, but a laser beam can give you a wavelength at the desired wavelength. So because you have what are called tunable dye lasers or OPOs that give you frequencies of any and at any wavelength in the visible or in the UV. I don't know if that answers your question.
Okay, I didn't see another question on the online forum, but if anyone wants to ask a question, you can either type it in the chat or unmute and come close to the speaker and unmute and ask your question.